the way that this goes is that this whole past few sections were all about what are called quadrilaterals. Quadrilaterals are broken down into two parts: non-parallelograms, and then the other ones are parallelograms. The first few days that we've dealt with this have been non-parallelograms, where we had rectangles and rhombuses and squares. We had all the different properties. The non-parallelograms, if you look at, are still what are called quadrilaterals, but those are going to be the trapezoid, the kite, and the isosceles trapezoid. And this one has the isosceles.
So a kite is a non-parallel?
What's that?
A kite is a non-parallel?
Yes, sir.
Say less.
Kites and trapezoids are all non-parallelograms, which means they have all different sets of properties to work with. So what I like to do is kind of just start with trapezoids. I know you guys have all worked with these. I know you guys have seen these. I know you probably know most of the properties. I don't remember the properties of a regular one. You're probably more accustomed to the properties of an isosceles. Well, let's just go through it real quick. So trapezoids. What do? They kind of hang out, act cool. You know.
What do they consist of?
4 sides.
All right.
They have one set of parallel sides. So trapezoids have one set of parallel sides. They can be vertical, they can be horizontal, it doesn't matter how they're written out. Bless you. But they will only have one set of parallel sides. I shouldn't have to play this 3 times every day. Why don't we take a notebook out and put all the other junk on the floor? That'll alleviate the issue. Right? I hate when I write. So, what happens a lot of times with trapezoids is that since you have parallel lines, you've got a transversal. These 2 angles on this side are always supplementary. Basically, the easy way to think of it is the angles between the parallel sides will always be supplementary because they're always going to be consecutive interior. Okay. So the 2 angles between these parallel sides, these 2 guys, will always be supplementary. They're not going to be congruent to each other. Those 4 angles are more often than not going to be all different. Because once they start being the same angles, then other things have to happen. So for the most generic way of looking at it, a trapezoid is just something that has one set of parallel sides. The fancier version of it, is called the isosceles trapezoid. You already know something about an isosceles triangle. Don't shake your head in disgust. So an isosceles triangle has what? Congruent base angles. What else? 2 congruent sides. Good. Now, an isosceles trapezoid is actually built from an isosceles triangle. So what happens here is that if you connect the midpoints, when you connect midpoints of a triangle, you create what's called a midsegment. You guys vaguely remember that? So the midsegment connects midpoints. So these 2 guys are the same. So now what happens here is that it's now a trapezoid because it's got one set of parallel sides and congruent legs. That's where it comes from. So the isosceles trapezoid, we'll write it out here. The isosceles trapezoid is more the style of one of these that you guys are accustomed to seeing. You guys are used to seeing that picture for a trapezoid. That's what you're used to seeing when we talk about trapezoid. The reason that they're isosceles is because of how they're derived, how they're created. They're created from an isosceles trapezoid. So isosceles trapezoid still has one set of parallel sides. It has congruent legs. And then two sets of congruent base angles. And the reason that that happens, again, if I could draw this back up, if I draw that back up, if you've got two parallel lines cut by a transversal, these two angles here and here would be corresponding. They'd be corresponding. Same thing here and here. Well, these two angles are the same, which makes these two angles the same because they're going to have the same supplement. So that's where all this stuff comes from. And that's where kind of you're going, not corresponding, you're going with consecutive. So these two will always be supplementary, just like they would be with any other trapezoid. Just so happens that these two are the same. So isosceles trapezoids have a bunch of stuff. I'll make a list here. We have one set, parallel sides. We have congruent legs. And you guys all understand when I call them legs are the ones between the parallels? I think I had to explain that one. I don't want to assume anything. The whole angle side. Two sets, congruent base angles. And the one thing I always overlook, it always has congruent diagonals. The diagonals of an isosceles trapezoid will always be congruent. Doesn't necessarily mean they have to be perpendicular or anything like that. It doesn't mean they're going to bisect any angles. It just happens to be that the diagonals themselves will be the exact same. And that all has to deal with slopes and why the slopes work. I'm sure you're really excited about that. Super exciting, right? Hey, remember that thing I just talked about called the mid-segment? You're right, it's the middle segment. Guess what trapezoids have? Mid-segments. I know, right? It's crazy. Mid-segments. Mid-segments and trapezoids. This works for whether it's an isosceles or a regular old boring trapezoid. It doesn't have to be isosceles like this way. Because remember, mid-segments, like we did this in a triangle, mid-segments are just segments that connect midpoints. Yeah, right? Segment connecting the midpoints. They're always parallel. If I call the bases of the trapezoid, you guys understand that I'm talking about the parts that are always parallel? So trapezoids have parallel bases. The mid-segment is always parallel to it. It's parallel to the bases. And it's equal to half the sums of the two bases. So that mid-segment equals half the sum of the two bases. So we throw in a little bit of algebra with this as well. But like we've said, it's nothing that you haven't seen and or done at any point in time in the square. So the mid-segment is half the sum of the bases. Remember when we did mid-segments before, one of the things we talked about was instead of taking half of something, sometimes you get ugly numbers, what would you do to get rid of the half? Yeah, you multiply the other side by 2. You multiply by the reciprocal. It's one way of getting rid of fractions. Comma where? Now remember, these are your bases. You have base 1, base 2. It doesn't matter which one's which. It's just you have 2 of them. So the mid-segment, another way of doing this is that you can always double the mid-segment, and it equals the sum of the bases. Just another way of writing it out. It looks really similar to what we did. We've done a lot of problems where you've taken halves of something and you just flip it around. This is actually something you guys have done, I think, in not so many words. We've done this about 3 or 4 different times throughout this semester. You did this when we found midpoints. You did this when we found missing endpoints of a midpoint. Remember how we say, here's an endpoint, here's a midpoint, did you go up or down? How much more do you have to go up or down, that kind of thing. You did that. We did mid segments in triangles. We had to we had to cut things in half. And now we're doing them in triangles. It's kind of one of those things that shows up a lot. Which means we can do some problems. For example, we have more stuff to write. We still haven't talked about kites, but we do some problems real quick for that segment. We'll go back into kites. So what we're going to wind up doing here, guys, is we're going to find a couple of different things. We're going to solve for x, and then we're also going to solve the missing segments. Now, these types of problems will always tell you whether or not you have a mid-segment. It'll say QR is a mid-segment, or in a diagram it'll look like that with the tick marks, showing that it is connecting midpoints. And like we've done before, I always like to start these types of problems out by writing out in words what we have, and then substitute in the algebra to solve. Because I think it's easier to see where things are coming from before we start mapping. So remember, the formula is mid-segment is half the sum of the bases. Well, which of those algebra parts is the mid-segment? It's the x plus 2. So x plus 2 has to equal half of the other two, 4x minus 10 plus 8. Okay. Order of operations tells you to take care of the stuff inside the parentheses first. So if I combine 4x minus 10 plus 8, I get 4x minus 2. Bless you. And now I just have to start making some decisions on how I want to finish solving it. Do I want to take half of the thing in parentheses, or do I want to multiply the other side by 2? going to take half of this one because both numbers in the parentheses are even. What's half of 4? What's half of 2? 1. So when I take half of everything inside the parentheses, it works out rather cleanly. We get x plus 2 is 2x minus 1. Okay. Had to look for a second, just want to make sure. Where'd I get the what? The 8? I can spotlight it for you if you like. Zoom in. You didn't know this did this, and I can go over here and go, put this or 2. Oh, I can also do this. You got it now? I know you said adjust there, so you can see figure that out. I can look over here. Whoa. And then I can say, oh, it doesn't work. 0 starts scratch. Oh, it's going great. You guys don't know this stuff happens? Subtract x, add 1. You get x equals 3. Better write it quick. It did? I don't see where the answer is. Alright. So you get x is equal to 3. And then I always like to go back and substitute in because dealing with mid-segments is pretty easy. 3 plus 2. 4 times 3. Subtract 10. 2. Alright. Now let's see if we can figure this out. Going from 2 to 5, do you go up or down? How many?
3.
What's 3 more than 5?
8.
Huh? Well, in this case, it's both the difference and the value.
Yeah.
It's not always going to be that. I see where you go. Okay. No, hello. Sorry. Just an average. Waiting. Oh, you're done. All right. Do the same thing here. TU is a mid-segment. Figure out what WZ TU equal, please. Take a minute or so and do it. By the amount of you guys not crying and whining about this, this probably means that you're doing just fine. So 2x and 10 is half of the. And once again, we combine this up in the parentheses first. Yep, you get 6x plus 6.
I think I know
Yeah, I know this is not one of those problems you can take half of it without having to worry at all, just because, you know, they're even numbers. Go figure, they're pretty nice on you sometimes. So you get 2x, 10 is 3x, 3. Dun, dun, dun. X is 7. So if you substitute back in there, 7 times 2 is? Add 10, you get 4. And then 42 minus 12 is 30. This is a 6. Sir. Get what? 2 times 7. Add 10. 6 times 7. Subtract 12. So I did. We found the value of x, and then I just took that value of x and I substitute that. All right, let's talk about kites. All right, fancy pants, you draw a better kite. Ooh. All right. Now, this textbook. So when we're dealing with guys, there's a lot going on with kites. I want to make sure we get through them real quick, so before we run out of time. I want you guys to think of kites. I think the easiest way to explain them is that a kite is made up of 2 isosceles triangles. The kite is made by 2 isosceles triangles that share a base. So if you have 2 isosceles triangles that share a base, well, isosceles triangles have congruent legs. The base, in this case, winds up being a diagonal. So these 2 will be the same. Those 2 will be the same. So a kite winds up with, I'll start making a list over here. Has 2 sets of non-opposite sides congruent. What I'm meaning by that is that the side, you have 2 sets of sides that are congruent, but they're just not opposite each other. They're 2 sets that are next to each other. That's where it comes when you think about it in terms of isosceles triangle. They have diagonals that are perpendicular. And now here's where things start to get a little bit weird. When you have isosceles triangles, and I know we've dealt with them a lot today, if I cover up this bottom part, when I have congruent legs, my base angles are the same. You guys okay with that? So that means that these 2 have to be the same here and here. For argument's sake, doesn't this now give us angle, side? So that means then all the other parts within these 2 triangles wind up being congruent. So this portion is the same as this. Obviously, this is the same because it reflects it. But up top here, that larger angle is bisected. Yeah. And if you look at the other part of the triangle, of the other isosceles triangle, it's the same exact thing. Since you've got congruent legs here, the base angles here are the same, which again gives you angle, angle, side, which means these down here are also bisected. So the diagonals do two things. I'm sorry, actually, within kites, diagonals do three things. Four, actually. I'm really counting. They're perpendicular. They bisect the diagonal between the two different sets of sides. So this diagonal here is bisected. The diagonal between the two different sides is bisected. Oops. The diagonal between the two same sides bisects the angle. So we have, they're perpendicular. The diagonal between the two different sides is bisected. The diagonal between the two same sides bisect the angles. Excuse me. And then the last little bit here, the angles between the two different sides are congruent. Angles between the two different sides are also congruent. Like I said, kites have a ton of stuff going on, but it's not that you have to look at every bit all the time. And to be honest with you, this textbook, I think the most they use is they're going to use the bisecting of the angles, and it'll use the segments on the outsides the most. It doesn't really get into too much of the other stuff. One other thing I will show you, real quick, you can probably see this now. How many right triangles are created here? Yeah. So the worst case scenario with right triangles is you might have to use a Pythagorean theorem. You might have a Pythagorean theorem part to figure out one of the segments on the edges or so. But they don't go any further than that. I know that looks like a ton of information, but when it comes down to the problems that we wind up doing with these, it's really easy. It really is. With it being a quadrilateral means it has four sides, what do all four of the outer angles have to add up to equal? 360. Okay, so that's one of the other properties you'll see come up pretty often. Can I go to an example? You're going to use this one? So if I have just these two here, and I ask you to find the missing angles, it's relatively simple. I beg to differ. Let's see. Two sets of lines and sides to the right. Perpendicular diagonals. Sorry, I didn't hear all that. Oh. In that first one, that 88 degrees is between the two sets of different sides, which means angle K has to be how much? 88. Again, it's just because it's between the two different sides. Well, how many degrees are in a kite? 360. So if I take 88, 88, I get 176. Add the 120 to it, you get 296. Yep. So that gives you how many left over for J? 64. Not drawn to scale. All you're doing is just adding them up and subtracting them. Same deal on the other one. The other one you have the 60 and the 50, which means that the last two angles of the kite have to be the same. So what's 60 and 50? It's that chair. I'm telling you. If you sat anywhere else, you wouldn't have said that. It's a square. 60 and 50 is how much? 110. If I take 110, I know that 360 is all of them. You're left with 250, aren't you? Which means each of those have to be the same, so I cut the 250 in half. You are at? There's a ton going on, but math-wise, it isn't trying to mess you up too much. I mean, at least it doesn't try to. You can't. Not terrible? All right. In this one, bless you, solve for x, and then find the missing angle. Take a second and go for it. Solve for x and find the missing angle.
Oh, this thing.
So what's x going to have equal? 5.5. X. So you get 55 and a half, and what's left over for that last one? 58? You guys agree with that?
Yeah.
Like I'm saying, not too terrible. We know that 2x. So if this is 110, that's 111, 111, that gives you 222. Add the 80, which is 302. That's where it goes from. Okay. Oh. Oh. You heard us? I heard the. It's a problem, the line of, oh, Murphy. Bless you. Sometimes you don't have to math as hard as you may think. And this one here, you've got a, oh, we're running out of time. Real fast, I'm just going to walk through this one. See how you've got mid-segments? And in the mid-segments, you have two numerical values of segments and one with a variable. When you see one like that, try to think of it mentally. It works out to be easier. For example, from 43 to 32, do you go up or down? Down, how many? 11. Okay. What's 11 less than 32? 21. So this side has to equal 21. With mid-segments. If you have numbers, because it's the same idea, you're going up or down, it works. It'll always work. You can do the formula and fill in the blanks, and you're still going to get to the same result, but that side has to equal 21. Divide it out, and I think you get 5 1/4. Homework-wise, it's in section 6.6. I believe it's page 394. I think the only screwball-y-ish one out of all those is actually 36. It's making you bisect one of the angles, and then you have to use triangle sum. How many degrees are inside of a triangle? Really all there is to that one. Work through these, and I would also probably make sure in your review packet you kind of got chapter 6 done. Then we can go over all of that on Monday to do our test then on Tuesday in chapter 6. That's kind of a good way to push things through. Okay. Super exciting.